So today we are talking more about instantaneous growth and or decay models. There, that's a nice straight line. So far the models that we've been working with have been periodic growth and decay models. So the periodic model looks like f of x equals CA to the t, right? And our growth or decay factor was A. And then the growth, well, we'll call it percent rate of change is R. Here, I'm being lazy. I'll write the word change. R. And then remember that the relationship between the two was that A equals 1 plus R. And then our initial value was C. So just like we talked about with interest yesterday, with these instantaneous growth and decay models, it's just what happens when we take a periodic growth or decay model and make the period of time at which the change occurs smaller and smaller and smaller and smaller, right? So yesterday when we did that half-life problem, we took the period of the decay from 24 years down to 1 year. So if we take that down to smaller and smaller and smaller intervals, then we end up with this instantaneous growth or decay model, which just accurately reflects the fact that these things are changing gradually, not in specified intervals. So an instantaneous exponential model, that's not an A, this should be an X, looks like f of x equals c to the, or times e to the RT. And we can use either one of these to model an exponential growth or decay situation, just depending on which one we choose to use. And I will tell you in the question, like on the test, which one to use. But what I want you to notice is that like the R is the same thing and the C is the same thing, like regardless of which model we use. R is still the percent rate of change. And C is still the initial value. So, for example, let's say that we had some substance. Oh, here, I should say it this way. We're going to start with 10 grams of a substance. And it grows at a rate of 12% per day. then I can write two models. So I can use this information to write either an instantaneous growth or decay model or a periodic growth or decay model. And we say C is equal to 10. R would be a positive 0.12. And so A would be 1.12. And so what the two models would look like are, if X is the number of days, I would have f of X equals 10 times 1.12 to the X. And then the instantaneous model would be f of X equals 10 times e to the 0.12 x. So just so you can see sort of the contrast between the two and how we use each of the values in the equation itself, notice that that initial value is always the coefficient. And then just how we use the rate is kind of the big difference here. And I mean, the fact that E is in there is a big difference as well. So I will tell you which model to use, but keep in mind that A and R, and the initial value, so A and R and C, they're all the same regardless of what model I'm using. So we can always get that percent rate of change from either of the models. Make sense? Okay. So, go ahead. So if we look at this guy, this periodic function says that I have 10 grams of the substance for 23.999999 hours, and then all of a sudden I have 12% more as soon as we hit 24 hours, so as soon as a day passes. And we know that's not really how things change or grow, right? We know that they grow gradually. So the instantaneous model takes that into account. It takes into account that it doesn't grow periodically, so it doesn't grow like every day. It grows at an interval that's so small that you can't even measure it, right? Because it's always growing. So it just makes it continuous rather than, so like if we think of it as a graph, a periodic model is essentially, and if you graph it, it doesn't look like this, but it's essentially saying, okay, I start here and I have this much up until this point, and then I have this much, well, and there wouldn't even be a line right here. So if these are days, so I have this much for the second day, and then I have this much for the third day. See what I mean? Like, it's like you have a constant amount all day, and then all of a sudden it jumps. Whereas an instantaneous model takes into account that we're actually growing gradually. So just like yesterday with the interest that we talked about, so if you're compounding once a month, that's different than adding interest all the time, like every instant, right? And so that's the main difference. Like when we graph the periodic growth and decay models, they still look like a continuous graph, but we're just making an assumption about the behavior of it, and so that changes how it actually grows or decays. And a lot of these things, you don't really see much of a difference between the two models unless it's on like a large scale or a really, really small scale. So like if you graph them, like if you graph the two models, like they basically look the same unless you zoom like way, 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 way out so that you can go really, really far to the big X values. But it does make a difference when it comes to things like, so like we said yesterday, like the difference in interest doesn't seem like that much when you like deposit like $100. But if you think about something like a mortgage that's like over 30 years and it's like a large amount of money, you know, in the hundreds of thousands or millions, then that little bit, the little bit of difference that occurs because of how often you compound actually makes quite a big bit of difference as far as how much interest you end up paying. And the same is true like when we talk about like bacterial growth or something like that. That little bit of difference doesn't seem like much, but when it's on like such a tiny little scale, then things are growing in the billions and billions and billions of bacteria, and so it makes a difference. Okay, let's talk population. I should preface this with telling you guys that population does not actually grow exponentially. It follows what we call a logistic model, which is like it grows exponentially for a while, and then you hit the limit of or you start to hit the limit of the resources that you have to support people, and so it starts to slow down. And like in the world right now, we're like basically we're like right here-ish, where like population is still getting bigger and bigger, but it's actually getting bigger at a declining rate, so a slower and slower rate over time, which wasn't true for a long time. I mean, like up until like the 2000s or so, like we were increasing at an increasing rate for a really, really long time population-wise. But so population, we're going to model population like in this problem as if it's going to grow exponentially forever. That isn't realistic, but since we're doing exponential models, I figure we'll just pretend. So New York City had 7.3 million people. Oh, I didn't say. I left an important word out here. In 2000. I apologize. And is increasing at an instantaneous growth rate of 9.8% per decade. So when we say instantaneous growth rate, we just mean that it's changing instantaneously, not actually changing every decade. Like, a certain number of people don't just get born and plop down in New York City every 10 years. So we want to think about first what our inputs and outputs are going to be, because they don't actually tell us. So they tell us that our input is going to be X, which is decades after 2000. And then our output, I think we should go ahead and measure in millions of people. That way we don't have to write a bunch of zeros. So we'll call it P of X equals New York City population in millions. Of people. Do I have to say that we're measuring people? We're all good with that? Okay. So all I really need for an instantaneous growth model is I need an initial value, and then I need that growth rate. So we have P of X equals C e to the RT, and C is our initial value, so corresponding to an X value of 0. So in the year 2000, we had 7.3 million people, and then our growth rate is a positive 0.098. In decay models, your growth rate will be negative, so you will actually put a negative number in your exponent, and they won't always give it to you as a negative. If they say a decay rate of 9.8%, you kind of have to deduce that means that R is going to be a negative 0.098 rather than positive. So we have P of X equals 7.3 e to the 0.098 x. And on the test, there's a couple things that I don't give you in the notes because I'm here to say them out loud. But on the test, I will tell you, I'll give you the model. So when I say to write an instantaneous exponential growth model, I'll tell you that it should look like this, just so there's no ambiguity about if you should be doing C times A to the T or if you should be doing C times E to the RT. So instantaneous takes care of that, but 2 days after we learn it, I'm not going to expect And then I will also give you rounding instructions. Rounding kind of makes a big difference on problems like this when things are growing really, really fast. Like 0.001 of a year makes a difference. But so I didn't give you rounding instructions on here because we can just say it out loud. But on the test, I'll give you rounding instructions so you don't have to stress about like how to round. Okay, so according to the model, let's find the population of New York City in the year 2050. So remember that our x value is measuring decades. So x is going to be what? 5, right? Because 5 decades since the year 2000. And so we want P of 5, which is 7.3 e to the 0.098 times 5. If you have a calculator that doesn't go up into superscript for the exponent, be sure that you're putting your exponent in parentheses. So like if you have a calculator that just goes like this, make sure you put that 0.098 times 5 in parentheses so that that whole thing is your exponent. I've noticed more than other things that we've covered this semester that just plugging things into the calculator can often cause errors, like just formatting that correctly. So make sure that you're writing this step so that I know that you did the right thing, even if you plugged it in your calculator and got incorrectly and got the wrong number. So what do we get here? So like 11.9 million?
Yeah.
We'll just go with that. And then according to the model, we want to know when the population is going to be 1 billion. So if we're given the population, we're given the output, how many million is a billion? 1,000, good. One way to think about that is that like you're adding another comma when you go from million to billion, so that's 3 zeros. So that's always true. Going from thousands to millions to billions to trillions, you're adding another 3 zeros, so it's a factor of 1,000. So we set 1,000 equal to 7.3 e to the 0.098 t. And then we will divide by 7.3 on both sides. Again, don't round in preliminary steps. So you're just going to leave that as 1,000 over 7.3 until you plug the whole thing into your calculator at the end. It's an ugly fraction and not one we would ever use as a final answer because it's a fraction and a decimal. But this way we don't have to round it before the final answer. So then we will take the natural log of both sides. So we have the natural log of 1,000 over 7.3 equals the natural log of e to the 0.098 t. And remember that the natural log of x and e to the x are inverses of each other. So this is one of the reasons we use natural log to solve exponential equations, because it works out really nicely when our base is e. These guys just undo each other. Another way you can think of that is that this is 0.098 t times the natural log of e, right, if you brought down that exponent. And the natural log of e is just 1, right, because 1 is the exponent you would raise e to get e. But you certainly don't have to write that if you remember that the natural log and e just undo one another. And so we get natural log of 1,000 over 7.3 equals 0.098 t. And then we'll divide by 0.098 on both sides, so we get t equals the natural log of 1,000 over 7.3, all divided by 0.098. So then plug that whole thing into your calculator all at once, and let's round to the nearest tenth. So to 1 decimal place. What do we get? It's going to be big, so if you get a fairly big number and you're questioning yourself, it actually is pretty, I mean, it's relatively big. I mean, it's not like a billion, but it's not like 5 years or anything like that. It's like 50, yeah. 50.2. 50.2. Did everybody get 50.2? So let's look at... 2,502, because that 0.2 is 2/10 of a decade, right? So that's 2 years, and that's why we rounded to 1 decimal place, so that we have the tenths there, because each tenth is just 1 year. Questions? Okay, let's do half-life. So last week when we started talking about half-life, we had our input be number of half-lives, right? So we had this periodic model that said things changed like every 1,000 years or every 24 years, or in this case, every 100 years. Yesterday we took it down to a year, but it was still a periodic model. It's still saying that you have the same amount for an entire year, and then all of a sudden, like a certain percentage of it disappears. And so we're going to take it now to an instantaneous model. And so we want to write a model CE to the RT that models the decay of a substance starting at 50 milligrams and having a half-life of 100 years. So in this case, we can't use a decay rate of 0.5, right? Because that's just every 100 years. And the period of time we're using here is in just years, and so this is a situation where we're just going to have to use 2 points to solve for our decay rate. So if we say t and what did I say, p of t, so the first point we'll use is just our y-intercept, yeah, so 0 and 50. And then what's another point that I know is going to satisfy this model? Yeah, 125, because we know that after 1 half-life, I have half of the substance left. So after 100 years, I only have half of the substance left. And so we can say C is equal to 50. So that gives me P of T equals 50 times e to the RT. And then we're going to plug our second point in and solve for R. So just like the ones you guys did last week where you plugged a point in and you solve for A, it's that same idea. And so we have 25 equals 50 times e to the R times 100. So we'll divide both sides by 50, which gives me 0.5 equals e to the 100r. And take the natural log of both sides. So natural log of 0.5 equals the natural log of e to the 100r. And so the natural log of 0.5 is equal to 100r. Because again, our base on the right side is e, so the natural log undoes it and just gives us that exponent. And so we have the natural log of 0.5 over 100 is R. And let's round that to let's round it to 3 digits, or 3 decimal places rather. What do we get?
-007.
Nice. 007. I didn't even do that on purpose. Okay, so, I wanted to mention also, like, on last night's homework, when it comes to rounding, always make sure that you go out enough digits that you don't end up with a 1 or a 0 for A or R, right? Like last night's, it was like 0.99967 something or other, or 57, something like that. And if you rounded that to 1, then that would be a constant function, right? Because 1 to any power is just 1. So you never want to round that A value up to 1. So like you would want to, on last night's, you would want to use like 0.9996 or something like that. And like same deal here, you wouldn't want to round this to 0 because then nothing is happening, right? There's no decay at all. Okay, so I need to write the model, that would help, right? Equals 50 e to the negative 0.007 t. So again, because this is decay, we're going to have a negative R value. That's what shows us that it's going down. So by what percent does this substance decrease every year? .7%. Yeah, so it's just your R value written as a decimal. So it decays 0.7% each year. I replaced the negative sign with the word decay. I could say it changes by negative 0.7% each year, or I can say it decays by 0.7% each year. So the word decay takes care of the negative. And then to go from a decimal to a percent, you just multiply by 100. And that's all it is. So how much of the substance is left after 16 years? So you guys figure out these two. Just like we did that last problem. Okay, so let's see. For part C, we just want to evaluate our function for 16 years. So we have 50 e to the negative 0.007 times 16. And that should be like 40 point, is it 40 or 44? 44, thank you. 44.7 milligrams. And if you're not getting if you're setting these up the right way and not getting the same numbers as we are when you punch it in your calculator, be sure to come see me or let me know, just so we can figure out how to correctly put it in your calculator, because that's sort of half the battle on some of these, is just getting it in there right. And then here we want our output to be equal to 10, so we set 10 equal to 50 e to the negative 0.007 t, and then take the natural log of both sides. Whoa, no. I'm getting ahead of myself, I apologize. We have to divide first. There we go. And so now we can take the natural log of both sides. And then again, on the right side, because our base is E, we just get our exponent. And so we get the natural log of 0.2 divided by negative 0.007, which is 229.9, you said? 919. Yeah, we'll just go to 9. Good. Years.
Do you have to divide the 50 right that under this thing right there? Or no? Can you leave it? Because I left it and it still got the same answer.
So it depends on what you did after that. Because so if you did the natural log of 10 equals the natural log of 50 e to the negative 0.007t, then you'd have to rewrite it as addition. Right, so this would be the natural log of 10 equals the natural log of 50 plus the natural log of e to the negative 0.007t, like that. So you have to use those, your logarithm rules. So you can do it that way. You just have to not mess it up if you do it that way. So then it would be like a subtraction. Like that. And then you divide. And that would get you the same thing. But it's a little easier just to divide first. Other questions on that one? Good. Okay, let's grow some bacteria. E. coli even. Fun stuff. So we're going to do the same thing as we did in the last problem, except in this case they just give us our second point, so we don't even have to figure it out for ourselves. So we know that I don't know why I keep using P, but we'll just go with it. We know that we start with 100 CFU, and after 2 hours, we have 13,300. So you guys go ahead and write your instantaneous model. So again, that's P of T equals CE to the RT, using those 2 points. And in this case, round to 3 decimal places. This one, so I'm putting the solution to A up here. Just make sure you check that before you move on to especially C and D. I didn't realize how late it gotten. We should go over these real quick. So all the ones I looked at had the correct answer for A. Yeah, look good. And then B is 244.5%, right? It's just your R value as a percentage, right? So multiplying 2.445 by 100 will give you that 244.5%. And then for C, we have P of 3, which is what? Anybody get that far?
153,302.778.
302 points, so like 303 work, okay. And that's in CFU per milliliter. And then if we set this equal to 1 million, and we really have to use 1 million because we're not counting in thousands or anything like that. So the 2.445 T, what'd you guys end up with? T equals 3.767? Yep. Okay, so tonight's homework is just another worksheet.